Hey everyone, and welcome to today's Explainer. Today we're taking a really fascinating journey. It's one that starts deep inside the incredible microscopic biology of our own vision, and then completely pans out into the massive, mind-bending physics of the sky above us. We'll be breaking down concepts from the human eye in the colorful world, touching on the absolutely brilliant foundations laid out by educators like Rita Singh. So get ready, because we're going to connect the micro to the macro in a way that is literally going to change how you see the world around you. I want you to start off by thinking about a couple of highly relatable questions. First, why do stars twinkle in the night sky while planets just don't? They just sit there with a steady glow. And on a more personal level, why does a biological masterpiece like the human eye suddenly require a piece of glass in front of it just to read a book or look at a whiteboard? As we'll see today, these everyday things aren't just random occurrences. They are absolute masterclasses in physics and biology working together. Okay, let's dive right into this. Here is our roadmap for the explainer. We're starting with the ultimate biological camera, then moving to the power of accommodation, vision defects and fixes, prisms and the color spectrum, and finally, atmospheric optical illusions. Let's kick things off with Section 1, the ultimate biological camera. Our eye is this roughly 2.3 centimeter sphere, right? And it is a compact piece of biological machinery that honestly outperforms practically any tech we've ever built. Let's trace the path of a single photon of light entering this biological camera right now. Step 1 is the cornea. That's the thin, transparent, bulging membrane at the very front. This is your gateway. And surprisingly, it actually does most of the heavy lifting for light refraction, bending the light before it even gets deep inside. Next, the light hits Step 2, the pupil and iris. Think of the iris exactly like the mechanical shutter of a camera. It expands and contracts to control the size of the pupil, basically determining exactly how much light gets in. Step 3 is the crystalline lens, which acts as the fine-tuner to perfectly focus that light. Step 4, the light hits the retina at the back. This is your biological movie screen. And finally, Step 5, the optic nerve grabs that image, turns it into an electrical signal, and zips it straight to your brain. Now, you might be wondering, why doesn't this little sphere just, collapse like a deflated balloon? Well, that brings us to two really vital fluids, the aqueous humor and the vitreous humor. And a super easy way to remember where they are is just simple alphabet logic. Aqueous starts with A, the first letter, so it sits at the very front, right between the cornea and the lens. It's a watery fluid that gives the eye nutrition and shape. Vitreous starts with V, way down the alphabet, so it sits in the very back, between the lens and the retina. It's this thick, gel-like substance that provides the heavy-duty structural support to keep everything perfectly inflated. So once the light pushes through that vitreous gel, it hits the retina. What's really wild here is the incredibly efficient division of labor happening on this biological movie screen. First off, because of the convex shape of our eye lens, the image that actually forms on the retina is real and completely inverted. Which means, yeah, you are technically seeing the world upside down right now. Your brain just flips it right side up in a microsecond, so you don't notice. But how do we see all the intricate details? That's thanks to our rods and cones. Rods control light intensity. They are your night vision specialists, working away in dim light. Cones, on the other hand, need bright light. A quick trick. C is for cones and C is for color. They are the sole reason you see a vibrant, colorful world. Moving right along to Section 2, the power of accommodation. So how does this amazing camera actually zoom and focus without us even thinking about it? This is called the power of accommodation. Unlike a camera's glass lens, which is totally rigid, your eye lens is flexible. It can change its focal length thanks to the ciliary muscles surrounding it. Actually, let's try something really quick. Hold your finger right in front of your nose and focus hard on it. Do you feel that slight strain in your eyes? That is the literal physical sensation of your ciliary muscles contracting to warp the shape of your lens. And this brilliantly illustrates exactly what's happening mechanically. When you view near objects, like your finger just now, your ciliary muscles contract and they squeeze the lens. The lens becomes thick and short, which decreases its focal length but drastically increases its focusing power. You are actively putting in work to see up close. But when you view far objects, like looking out at a distant horizon, those muscles completely let go. They relax. The lens stretches out, becoming thin and long. The focal length increases and the power decreases. So looking far away is literally a relaxed state for your eyes. But there is a hard limit to this power. Take a look at this number, 25. For a normal, healthy eye, 25 centimeters is your near point. It's the least distance of distinct vision. If you try bringing an object closer than 25 centimeters, the ciliary muscles they can't squeeze the lens any further, and the image becomes totally blurry. Meanwhile, your far point? That stretches all the way out to infinity. That brings us to Section 3, Vision Defects and Fixes. Of course, biology isn't always perfect, right? So let's look at the common glitches in our internal camera and how the brilliant science of physics steps in to save the day. Here are the two most common defects side by side. Myopia, or nearsightedness, means you can see near objects just fine, but distant ones are a blurry mess. This happens because the eyeball is slightly too long or the lens is too thick, causing those distant light rays to focus in front of the retina. To fix this, we put a diverging concave lens, a lens with negative power, in front of the eye to spread the rays out just a tiny bit before they enter. Conversely, hypermetropia, or farsightedness, means the eyeball has shrunk a bit or the lens is too thin. The image is desperately trying to form behind the retina. To pull that focus forward, we use a converging, convex lens with positive power. Now, to lock this into your memory for good, let's use a delightfully bizarre mnemonic for myopia. Okay, imagine this. Elon Musk eats way too much mayonnaise, gets thick, and hides in a cave. Hear me out. Mayonnaise stands for myopia. Elon reminds us of the elongated eyeball. Sick reminds us of the overly thick lens. And cave, well, that tells us the fix is a concave lens. It's super silly, but I guarantee you will not forget it on your next test. And we've got an equally fun one for hypermetropia. Picture a grandfather, a Dadaji, riding on top of a fast metro train. He shrinks his eyes from the intense wind, and his face stretches way back like wax. Fast metro stands for farsightedness and hypermetropia. Shrinks eyes reminds us of the shrunken eyeball. Face stretches stands for the long focal length, and wax, that gives us the convex lens fix. Aside from the actual shape of the eye, age brings its own natural hardware changes. Presbyopia happens as we get older. Those ciliary muscles we talked about, they lose their flexibility. That makes it hard to squeeze the lens for near vision, which is exactly why older adults eventually need reading glasses. And then there are cataracts, which occur when the previously transparent lens becomes milky and cloudy due to protein buildup. But the good news is, that's a condition entirely fixable today with a really standard quick surgery. All right, let's move to Section 4, Prisms and the Color Spectrum. Let's see how all this builds into something even more beautiful. Now that we understand how our eyes actually capture light, let's step outside and observe the colorful external world. Our eyes perceive white light from the sun, but as we know, white light is secretly a hidden rainbow. Dispersion is the splitting of that white light into its 7-color spectrum. If you shine light through a standard flat parallel glass slab, nothing much happens visually. But if you shine it through a prism, the unique non-parallel angle of the glass bends different wavelengths of light at entirely different angles, fanning them out into a massive spectrum. To understand exactly how it fans out, just look at this Vibgyor table. There is an absolutely crucial inverse relationship here between a color's wavelength and how drastically the prism bends it. Red light has the longest wavelength, so it basically just powers right through the prism, bending the least. It stays right near the top of the spectrum. Violet light, on the other hand, has the shortest wavelength. It struggles through the glass and gets bent the most, ending up all the way at the bottom. And all the rest of the colors? They fall perfectly in between. Finally, Section 5, Atmospheric Optical Illusions. Now for the grand finale. Let's explore the macro scale, where the Earth's atmosphere itself plays incredible tricks on our newly understood vision. We've seen refraction inside the tiny cornea and in a glass prism on a desk, but what about the entire sky? Enter atmospheric refraction. You see, our atmosphere is not uniform. It's a chaotic mix of shifting layers of hot air and cold air. Cold air is optically denser than hot air. Because these layers have completely different refractive indexes and are constantly swirling around with the wind, any light passing through them is continuously bent, distorted, and flickered before it ever reaches our eyes. So the crucial point here is that the sky above us is basically a giant, shifting, completely unpredictable lens. Let's rapid fire through some of the everyday illusions it creates. Why do stars twinkle? Well, because they are so incredibly far away, they act as tiny point sources of light. As their light cuts through those shifting atmospheric layers, the beam bends rapidly side to side, so the light hitting your eye literally flickers. Why don't planets twinkle? Because they're way closer. They act as larger, extended light sources, so the shifting beams overlap and just average out, creating a steady glow. And the most mind-bending illusion of a whole bunch? The atmosphere actually bends sunlight around the physical curve of the Earth. This means we see the sunrise a full 2 minutes before the sun physically crosses the horizon. And wild as it sounds, we continue to see a delayed sunset for 2 minutes after it has physically dropped below the horizon. It really makes you reconsider what you're looking at every single day, doesn't it? So I'll leave you with this provocative thought. The next time you're standing outside, taking in a beautiful, vibrant sunset, ask yourself, are you seeing the sun where it actually is?